Welcome back, everyone. After last week, we talked a lot about conditional probability and different ways of counting the different outcomes of particular experiments. This week, we're going to expand a little bit more on the probability discussion and start to, as you will see before the next few weeks are over, start to, again, as I've promised, link it to statistics, right? Link it back to what we were talking about before. Do recognize that you'll have a test next week after these two sections. And then we will pick back up in chapter 6 following that, where we will really put these two things all the way together into one general idea. But this week, I'm going to show you something about random probability experiments or random variables, right? And you'll be able to kind of learn how some of these probabilities work out in real life with some of the activities that you get to do in Excel. And so we'll do a bunch of examples this week. And I'm going to try to show you an example in Excel for the next section. And there's also some helpful examples in some of the other videos that are in this week's playlist that are from my previous classes. Let's see where we are, right? This week, or at least in this section, we're going to talk about random variables and discrete probability distributions. It sounds, there's a lot of words there, okay? But we're going to talk about how to construct a probability distribution. It's pretty straightforward once you get the idea. And then we'll talk about how to find the mean, the variance, and the standard deviation, which is actually much easier than some of the other stuff that we've done. And then I'm going to show you how to solve some application problems by calculating the expected value. And the expected value is kind of what you think, and we'll talk more about that in just a few minutes. Random variables or variables that are the result of random probability experiments, right? So flipping a coin, right? You flip a coin, 30 times in a row. How many heads do you get? How many tails do you get? Okay? Or you roll a die. Right? How many times do you get a particular number? Okay, what's the sum of the two? If you roll a pair of dice, right? What's the sum of the two? Okay, whatever outcome it is that we're looking for in this particular case, we just write as X. Okay, so X is the number of things that we're looking for, okay, or it's the event that we're interested in. Discrete random variables are ones where we have outcomes that we can count, and we can list all of them. Okay. There's essentially a countable whole number of outcomes, right? So for example, we're going to flip a coin 30 times. We could count all of the outcomes there. It would take a little while. Right? If we could roll a die 30 times, same thing. Okay. Continuous random variables are variables that can take on any value. And so something that could randomly occur, but it can still be a decimal. Right, so if we're randomly choosing people and we're measuring their height, okay, this is going to be a lot harder to predictably, it's going to be a lot harder to predict directly because there's an infinite number of values, right? We really can't count all of the possible outcomes. Okay, this is where we're going. Okay, as we talk about discrete variables this week, which is where we're going to focus this week. Okay? And we get into continuous variables after the next test. Recognize how we're kind of doing the same things. It's just slightly different when it's continuous. And we'll talk about that. You learn a few of the calculations in the opposite way. But that's why we're going to come back to some of the probability stuff. A probability distribution is kind of what it sounds like. It is just much like a frequency distribution, right? It's just a distribution of the probabilities based on all of the possible outcomes. Okay, it just provides whatever the distinct probability is for each of the outcomes that are possible. Okay, and you know which outcomes are possible because you can count them. They're discrete. Okay. You can then use these distributions to determine the expected outcomes in a probability experiment. You'll see kind of how that works, but it'll also kind of intuitively make sense too, right? Because it'll be how you understand it to be when you measure the probability of something. And we'll talk more about that as we go. These are very important things to recognize when we talk about probability distributions. Also, because when you calculate these things, it will help you catch if you make a mistake. Just remember that the probability can only be between 0 and 1. It will not be greater than 1. It will not be less than 0. Okay? And then the last one's really important. If you add up all of the probabilities of the distribution, it should be equal to 1. Right? You should be explaining every outcome. If you're not explaining every outcome, right, then something's missing. Right? There's a probability missing or something like that. If all the probabilities are there and you're explaining every outcome, then the probability that you can, write the outcome essentially is 1. So it should all add up to 1. It's just like the relative frequency. It should all add up to 100%. So let's take a look at some examples here. Fair coin is tossed twice. Okay, we're going to let X be the number of heads that comes up. Okay, so we want to find the probability distribution. And so if you flip a coin twice, there's only so many outcomes you could have, right? We flip the coin the first time, and you get heads or you get tails. Okay, and then on the second flip, you get heads or tails, heads or tails. And so 4 possible outcomes if we flip a coin twice. Okay, you can either get heads twice. Okay, you can get heads, tails. Okay, you can get tails. Okay, and notice that I put those 2 in the middle together because each outcome has the same number of heads. Okay, so each has 1. Okay, so there's one possibility that we flip the coin twice and get 0 heads, or we get heads 0 times. Okay, and so 1 out of 4, our probability here would be 0.25. Here there are 2 outcomes where when we flip the coin twice, we only get heads once. We get 1. Okay, and so 2 out of 4, the probability here would be 0.5. 50% of the time, you're going to get heads and tails, right? That should make sense, right? When you flip a coin twice, you're likely to get 1 heads and 1 tails. And then there's also a possibility that you get heads twice. And again, that's very much like the first one. 1 out of 4, or 25%. Notice if we add all these probabilities up, they will equal 1. Okay, we've defined all of the different outcomes, right? We can use the counting tree that we used before. And this is not something that you have to use all the time. There's different ways to figure these out. In some cases, depending on what the probabilities are, but it's just easy to use on the smaller examples. Okay, so we're going to hold on to this for just a minute. I think we're going to use this distribution here in a second. Oh, nope, take that back. So focusing again on the fact that all the probabilities have to add up to 1. We want to find the missing value in this table. Okay, so here's a table here's our event X. I don't know what the things are, but these are the possible outcomes. Okay, and these are their probabilities. Now we know if these are all the possible outcomes, then the probabilities have to add up to 1. Okay, and so we can basically just say 1 minus everything that's here. 0.5 and 0.25, that's 0.3 is 0.4, so 1 minus 0.7. So this has to be 0.3. And now they'll all add up to 1. So let's take a look at this example here. We have a probability distribution of a random variable that represents the number of extracurricular activities a college freshman participates in. Okay, so X is the number of activities, 0 through 4, and then the probabilities are given for each one. We want to find the probability that a student participates in exactly 2 activities. Okay, so if we randomly choose someone, the probability that they're going to participate in exactly 2 activities, well, that's this probability here. And so that's just 45% or 0.45. Okay, let's take a look at the next one. Find the probability that a student participates in more than 2 activities. Okay, well, more than 2 means 3 or 4. And so the probability of 3 is 0.21, the probability of 4, 0.14. We can add these up. Oh, I was trying to divide, no dividing. Add them up, we get 0.35. And we're 35%. And so the probability of more than 2 is just the probability of 3 plus the probability of 4. Because there's a 21% chance we could randomly choose somebody with 3, 14% we could randomly choose somebody with 4, 35% we could choose either one. Find the probability that a student participates in at least 1 activity. Okay, well, at least 1 means 1 or more, right? 1, 2, 3, at the smallest 1. So all of these. And now we can add all of those up. But again, remember, they should all add up to 1. So we can just say 1 minus the probability of choosing 0. And there's a 94% chance. If you add all these up, you should get 0.94. A 94% chance that you randomly choose a participant or a student who's in at least 1 activity. Okay, so let's look at another one of these. Here we have 5,000 undergraduates registered at a college. Of them, 478 are taking 1 course, 645 are taking 2, okay, 568, 3, so on. Let X be the number of courses taken by a student, okay, and randomly sampled, and we're going to find the probability distribution. Okay, so our outcomes, they could be in 1 class, 2 classes, 3 classes, 4 classes, 5 classes, or 6 classes. To find the probability, we've just got to do a little bit of division here, right? So there are 5,000 total students. 478 are taking 1 class. Remember, 478 divided by 5,000. That will give you, grab the calculator, 0.0956. And then we can do the same thing for the next ones. 645 divided by 5,000, 0.129. 568 divided by 5,000, 0.1136. 1864 divided by 5,000, 0.3728. I guess I could write 1 or 2 of these in. That might help. 1357 divided by 5,000. That'll give you that probability, and then 88 divided by 5,000. .2714. And 88 divided by 5,000 is 0.0176. Okay, so this is our probability distribution. Okay. A probability distribution is always going to be a table that looks like this. Okay. Or as you'll see in your Excel activity, a histogram that represents the table, much like a frequency distribution. Now we want to find the probability that a randomly chosen student is in 3 or more classes. Okay, well, 3 or more just means 3 or above. Okay, so there's 2 ways we can do this. We can either say 1 minus the first 2, okay, or we can just add up all of 3, 4, 5, and 6. 0.1136 plus 0.3728 plus 0.2714 plus 0.0176. Then we should find 0.7754 or 77.54% probability of choosing an undergrad, randomly choosing an undergraduate who's in 3 or more classes. The probability of more than 3, okay, now you have to kind of be careful here. There is a difference between 3 or more and more than 3. More than 3 means 4, 5, or 6. And so we would just add up those last 3. And that'll give us a smaller answer, smaller probability. So they are different. If we just add up the last 3 values, I'm sorry, I was adjusting it. My calculator, 0.6618 or 66.18%. The next question is about whether it would be unusual for a student to be taking 6 classes. Okay, remember, we said that things that happen less than 5% of the time are generally said to be unusual or rare. Okay, and that's where we're going to consider it to be in this class. And so would it be unusual for a student to be taking 6 classes? Well, this is less than 5%. And so, yeah, it would be. There's only a 1.76% chance of choosing that. Now we want to find the probability of choosing less than 6. I'm going to change the color again real quick to something slightly different. If we want to find the probability of less than 6, well, that's 5. That's not going to be good. It's 5 or below, right? And if we want to use the rule of complements to find the answer, then we can just say 1 minus the probability of choosing 6, which is 0.0176. And that will give us 0.9824. Here, a 98.24% chance that you randomly choose a student with who is enrolled in less than 6 classes. So as you can see in these particular situations, there are some probabilities that are more likely than others, right? Depending on how the samples work out. In the next situation, you'll see, or the next section, we'll talk about how you can deal with random outcomes where they're not, we're not using sample sizes and things to calculate the probabilities. Okay? But in both cases, we can calculate a mean of the probability distribution, a mean of the discrete random variable that we're trying to measure. Okay? And we do that by just multiplying the outcome times the probability. Okay? And then this is just a sum. We're just going to add them all up. And so x1, be x0 times the probability of 0 plus x1 times the probability of 1, and so on. Okay? And you would just add all those up. That's what the sigma means. It's relatively straightforward when you are just trying to calculate it from data, as you'll see in the next section. Okay? Because there's no dividing, right? There's nothing like that. You just multiply the two together and add them up. Okay. And we write this mean with a little x beside it. Okay? That's the expected value of x. Okay? It's the expected mean of x. the expected average value, if you will. Okay. You generally refer to the expected value because we're talking about things that haven't happened yet, right? These are not probabilities that we've measured. I'm sorry, these are not outcomes in particular experiments that we've measured. We're trying to predict what's going to happen, what we would expect to find based on some knowledge of the probability. Okay. Just like you'd expect, one heads and one tails if you flip a coin twice. If you flip it 100 times, you'd expect 50 and 50. Right? And so it's just a way of figuring out how to determine what you would expect before it occurs. Okay, so here's that probability distribution again from that previous example. All right, let's find the mean here. What is the expected value of the number of classes that students were enrolled in? So if we randomly choose a person, what's the expected value? What do we expect to get if we randomly choose someone? Okay, and so all we're going to do is just multiply all of these and add them up. Okay, 1 times 0.0956 plus 2 times 0.1290. I'm going to write all this out, you guys, but then I'm going to kind of skip to the answer because I've already got it written down. 4 times 0.3728. I've run out of space, plus 5 times 0.2714 plus 6 0.0176. Okay, and you would just add all of these terms up. Okay, the mean, the expected value of x, is just the sum of all of these particular values added together. And if we add all of these values together, you should get 3.6482, or about 3.65. And so, I mean, if you randomly chose a person, you'd expect there to be their classes to be somewhere between 3 and 4, which makes sense because that's where the largest probabilities are. We can also find the variance and the standard deviation of these discrete random variables, but this is a lot simpler to determine. Well, the variance is a little tougher to determine in this case, okay? But the standard deviation is still just the square root. And so now if we want to find, well, let's see, I think we're on the, oh, here we go. Let's find the mean, the variance, and the standard deviation here for each of these, okay? If we want to start off with the mean, right, or the expected value of x, it's going to be x times p of x, so 13 times 0.08, plus 14 times 0.24, plus 15 times 0.23, and so on. I'm basically just reading to you guys at this point, but we're going to write all of this out. That's 0.03. Okay, and if we add all of these, multiply and add all of these up, you should get 15.25. Okay, so this is the age of students at a public high school. So if we were to randomly choose someone, we'd expect them to be around 15. It's going to be the most likely outcome, essentially, is that they're somewhere around 15 or 16, somewhere in here. And again, you can look at the probabilities and kind of see that. Now we want to find the variance. Okay, the variance is a little bit more of a challenge. Okay, we write that as a sigma x squared. Okay, this is the sum of x squared times p of x, and then we're going to subtract the expected value squared. Okay, this is the easier format of that formula, and it just involves another sum. And so we're going to say now 13 squared times 0.08 plus 14 squared times 0.24 and so on. 15 squared, 0.23, 16 squared, 0.28, so on, plus 18 squared. Okay, and then once we get it to the end of the sum, then we're going to subtract away the mean squared. Okay, so 15.25 squared. And that will give us the variance. If you work all of this out in the calculator, you should find that you get 1.6075. And that is your variance. And then we can find the standard deviation, which is just sigma of x, by taking the square root of the variance, which is just the square root of 1.6075, or 1.268. And so for this probability distribution, we have an expected value, we have a mean, and we have a standard deviation. Call it 1.27. And so with the mean and the standard deviation, and what we talked a little bit about, if you think about the empirical rule that we talked about before, most of the data should fall within 2 standard deviations, and that's exactly what you see here. We're going to see a lot more of how all these things come together soon. Let's look at a few examples of how we can use this to apply to other situations, right? Where we're not just counting outcomes. We're not just counting numbers. An insurance company sells a 1-year term life insurance policy to a 70-year-old man. The man pays a premium of $400. Okay? If he dies within 1 year, the company will pay $10,000 to his family. Okay, according to the CDC, the probability that he's still alive after 1 year is 0.9715. Okay, we're going to let X be the profit made by the insurance company. Okay, so there are 2 possible things that can happen here. Right, there are 2 probabilities, if you will. Okay, but remember now, X is our profit. Okay, so we have to think about that. It's just not about whether the man is still alive or not. Okay, it's going to be our profit. So we're going to talk about that second. Let's talk about the probability first. Okay, the probability that he's still alive is 0.9715. So the probability that he is not still alive is 1 minus that. 1 minus 0.9715, 0.0285. Okay, so now let's look at the profit made by the insurance company. Okay, the expected value of the profit. So if he lives, he paid $400 and the insurance company pays nothing. Okay, and so the profit for the insurance company, if he's still alive after 1 year, is $400. If he is no longer alive after 1 year, he still paid his $400, but then the insurance company pays out $10,000. Their profit minus $9,600. They lost $9,600. If he dies. This is our probability distribution. Only 2 possible things. He either lives or he doesn't. Now look, we can find the expected value in this case. Okay, so the expected value of X is just X times P of X, and we're going to add them up. 400 times 0.9715. Right, they'll make $400 if in 97% of the time, essentially. And they'll lose $9,600 a little less than 3% of the time. What do they expect to make in terms of their profit? Well, 400 times 0.9715, 388.6, 9,600 times 0.0285 minus 273.6. 388.6 minus 273.6. The insurance company can expect to make $115 overall, right? So if this was one person, okay, they can expect to make $115 after a year. Because there's a good chance he'll be alive, but he might not be. If this were a whole bunch of people, and so we start adding more and more people, well, there's more and more chance then that most of those people are alive, right? And then over time, if we did this repeatedly, right, they would start to find that they could expect to find about $115 for each person that they have in the sample. It would be about that much because they'd get 400 most of the time and lose 9,600 sometimes. Right, and so it'll all kind of work out to where they would get about this much per person. But that's their expected value of the profit from this life insurance deal with the guy. Okay, let's look at one more of these. These are fun. An investor is considering a $10,000 investment in a startup company. She estimates she has a probability, 25% probability of losing 20,000, 20 making 10,000, okay, probability of 0.15 of 50,000. Okay, so they're just explaining the probabilities here. What's the expected value? Okay, and then what would you advise them to make the investment? Well, the first thing that we need to do is find, we need the probability distribution, and we need X, which will be our profit again. Okay, and then P of X will be the probability. Now they're going to invest $10,000, so they're going to put up $10,000 regardless. Okay, 25% probability of losing 20,000. So you put in 10 and you lose 20. Okay, so that's not the most useful outcome, right? So okay, well let's in this case. You would lose 20,000. Right? And the probability is going to be 0.25. I think we're going to come back to the investment amount. Though I think we could have factored it into. We're going to do this slightly differently. The probability of a $10,000 profit, so you're going to make 10,000, right? There's a 20% probability there. There's a possibility of 50,000 at 0.15. Okay, and then there's a 40% probability that you just break even, that you don't make anything. Okay, we're talking about profit here. That's why we're not going to consider this investment. We'll talk about the investment in a second. I confused myself with this question. So now we want to find the expected value. Negative 20,000 times 0.25, so on, 10,000. Okay, and it's important to keep things like losses and profits separate here. And so if it's a loss, it would be negative. 50,000 times 0.15 plus 0 times 0.4. Okay, and if we multiply all of those and add them all up, the expected value of the investment is $4,500, or the expected value of the profit. Okay, and so if you invest $10,000, you can expect that you'll make a profit of about 4,000. There's a chance you might, not at all. But if this were to happen over and over and over again, right, you would find that it would, level out to $4,500 for each person who invested 10,000. They would make that much money. Okay, because this is what we'd expect based on the probabilities. That's the end of this section where we're just talking about discrete probability distributions. In the next section, we're going to put this discrete probability distribution idea together with some probability experiments, as opposed to being told what the probabilities are, as we've been in this section all the whole time. Right now, we're going to calculate essentially real-world probabilities based on their outcomes. And I'm going to show you some things in Excel that should help you with answer some of these questions.